All right, so let's go to this. This is a fun, short, I mean, I think relatively cool chapter on urinary system. And if we end up, by some chance, and I doubt we will, but if we do have extra time at some point, I would probably go back and make sure that I could do that, to go over that respiratory. I mean, go back and do nutrition with y'all again. Because that really is one that I wish we had. I was actually excited thinking we had that. I'm going to spend the whole week on that because I covered 50 minutes, as you can see from that video, but it's intense. Okay, it is extremely crazy. Okay, all right, so let's go to this. This is kind of a cool one, and it kind of goes back to what we were talking about with the chapter on metabolism. Okay, let's make sure. I'm going to go off script here real quick, but let's just make sure. Now, what is this chapter about? Okay, check this out. If you remember, C6H12O6 sugar plus oxygen is going to be broken down into 6 carbon dioxides, remember, 6 waters, and we make 36 to 38 ATPs theoretical. You know, and I think I told y'all that would be a holy grail of biology for my whole life. We've been talking about this my whole career, and then somebody got around to checking this about 8 or 9 years ago, and no one's ever measured more than 30 on a cell. So that's very disturbing for those of you that go to church. This would be like finding 5 more commandments. You know, the 10 commandments of Moses dropped a slave that had 5 more. That's really disturbing to me because this is one of the holy grails of bioscience, biology. And so it's theoretical yield, and that's to keep life on Earth. So all living things on Earth break down sugar. Sugar is the food of choice. And so this is kind of lead in this. But if you have fats or proteins, you can convert them to metabolites that will fit in this pathway. So when we eat protein for fats, they ain't nothing but carbons anyway, right? Fatty acids and glycerol is 3 carbon sugar and long carbon chain. So they can be shuffled into glycolysis, transition, Krebs, and ETS. I'm reviewing 23. But when we eat proteins, look at this. Proteins all have that. This is the structure of the 20 amino acids, have a carbon in the middle, a hydrogen. Then they have this R functional group that's different. And then they have a amine group, an NH3, and a carboxylic group. Okay, now all of this is pretty much going to be carbons, but this little amine group is a problem. So when we eat proteins, we break that off, and that's called deaminate. And then grab the hydrogen and becomes ammonia. And if y'all know anything about chemistry, if you want to kill somebody, take some ammonia and shoot them in their veins, and they'll die in just a few minutes. Ammonia is very deadly to life, living organisms. So we've got to do something with that. And so our liver takes carbon dioxide and this, and we're breathing carbon dioxide out anyway, and makes a compound called urea. And then urea is the main component in, I was going to have that guy tinkling, urine. So really, I mean, think about it. This is kind of one of those things that we have to tie things together at this point at A and B. So the whole purpose of the urinary system is to get rid of nitrogen waste, and the main one is the breakdown metabolite of protein metabolism. So like I was telling y'all the other day, or in the lecture, y'all didn't get to, I haven't watched yet. That's okay if you haven't watched it. I mean, it's okay, but watch it. But when we got high-end athletes in here that run and they do all kinds of stuff. But if you ever exercise really intensely, and then the next day go to the bathroom and you've got bright yellow, you can smell it. It smells like urine real strong. That's because you had some meat before you did your sports event. You had some protein or chicken or something or beef. But if you go out on Friday night and have 8 margaritas and 18 pretzels, you know what I'm talking about? A bunch of beer. What does it look like? Water coming out, right? Because you hadn't had no protein. So it's real clear because the main component other than water is urea, and that's where urine gets its name. And that is a breakdown product of protein metabolism. Okay? Now, not to throw anybody off, but that's kind of the preface of this chapter, right? Is that's what we're doing here. Okay? Now, real simple stuff to begin with. Who are the players here? Well, let's take a look. The players of the urinary system are 2 pairs of kidneys, right? Which are going to be the filters of the blood for these nitrogen waste. 2 ureters that are tubes that connect the kidney to the bladder. Then the urinary bladder, which is storage of the urine, right? And then a urethra that comes out, right, to get rid of this urine from the body. Okay. Now we'll talk about this later on. We're going to look at reproduction, but remember, in the boys, it comes out the penis. It has dual function. In the girls, you have 3 openings down there, right? We'll go bottom up: anus, vagina, urethra. Okay. And so the urethra comes out, and it does not have a reproductive function in girls. It's simply urinary in girls. But in boys, the urethra is in the penis for reproduction and for urinary. Okay, that's kind of cool. Probably one of my favorite moments of teaching. Some 15, 20 years ago, a girl raised her hand, arguably she only had 2 openings down there. I was very nice, but she was just adamant, and I finally said, hey, would somebody let her borrow a compactor, or I'll buy it for her and let her go explore herself, just go look. And sure enough, she came back later, no glad she had three. So there we go. But there are birth defects where some people have two, and she needed to know that, right? So it was a cool teaching moment, but since you brought it up, I said, that's pretty standard, but there are people who have the vagina opens up in the urethra into the vagina, and that can be a real problem, okay? Have lots of kidney infections, et cetera, et cetera. Anyway, so there's your test question, right? List the components of the urinary system in their proper order. Okay, and there we go. Your kidneys, pair of kidneys, ureters, urinary bladder, urethra. Okay. All right. And of course, I think I have to jump the gun here. It should have talked about the functions here. Okay, here we go. Let's go back and get the functions here real quick. I think I've skipped those very quickly. But obviously, the main function is what? To filter the blood from metabolic waste, mainly nitrogen-containing waste. Okay, the main one being urea. But we also make uric acid, which is a breakdown product of nucleic acid metabolism. Okay, and there's others, other metabolites in there. Creatine is in there too, and of course a lot of electrolytes. So we got a lot of electrolyte balance. There's a lot of obviously sodium in urine. That's why you can't drink urine. It's extremely hypertonic. It has so much salt in it that if you try to drink it, like the guys in World War II to get the ship got sunken in a boat, and you cannot drink urine. It'll kill you. Okay, or it will dehydrate you severely. But we regulate the fluid electrolyte balance of the body by eliminating certain ions and water, or by reabsorbing water. So we thereby control blood pressure here. Blood pressure, right? It's a huge thing here. If you have high blood pressure, you take diuretics, right? And they will make you urinate. And remember, I know we said this before, but blood pressure is like tire pressure on the car tire, right? If you open and let air out, pressure goes down. You urinate, pressure goes down. So urinating is going to lower blood pressure. And then, because if you remember, we talked about how we're going to see in the kidneys that we can actually excrete hydrogen ions into the urine. Okay, so we can actually control pH here, and by reabsorbing or not bicarbonates back in the blood, eliminating or reabsorbing hydrogen ions and bicarbonate, we control pH of the blood. So super important for homeostasis of blood pH, and it also thereby directly influences blood pressure, right? And it makes one hormone called erythropoietin, which is the hormone that causes the bone marrow to make red blood cells, which is the first $1 billion drug for the biotech company Amgen that made them gazillions of dollars that allowed them to be the largest biotech company in the world. So that was the signature drug of theirs that started the whole process. In 1980, 92, when I came to work, I almost bought shares in it. They had 200 employees. Today, they probably have 200,000 or 300,000 employees. It's the largest biotech company in the world. Or if not, it's top 2 or 3. But that was their first home run, the Grand Slam. It also, other metabolic functions, to detoxify some things, activate vitamin D, can even make some glucose in some instances. Okay, so bean shape, structure, and let's get into that. So here we go. We're going to cut him open. Okay, and here's the anatomy of it. Okay, location there, been there, done that. Okay, 150 grams. I think we made a joke in here, and I think they're loud, and I think maybe Laura looked it up, but there ain't nobody hardly eating this thing. Okay, I've never seen anybody eat a kidney of any animal. It's not a high level. Look at liver. I mean, I love fried livers. Chicken livers is good, right? Anybody like chicken livers? Ain't nobody eating no kidney, okay, in America that I know of. Okay, now maybe somebody in another world, because ain't no meat in here. It'd be like eating a big table of salt, okay? Because it's mainly going to be a lot of salt in its tissues, but no muscle here.
It was said to have a lot of vitamins in it.
Yeah, probably. Okay, but I would think I'd really get them somewhere else.
Yeah, because back in the day, if a family could afford to buy an animal,
they didn't waste money or anything.
Right. So that was part of it.
But I think it would be dangerous. It could be not good to eat. Okay, because they just don't smelly thing we dissect.
Definitely not allergies.
So we cut them in lab a couple weeks ago like this, right? And notice that there are 3 big areas. There's an outer region called the cortex. Okay, then there's this middle region called the medulla, kind of where the pyramids belt down. That's part of that one, right? And then we got the pelvis, the yellow area. So cortex, outer layer, I think I went too far with that. Cortex, medulla, and then yellow is pelvis. Now, what we're going to see is that the functional unit of the kidney is a structure on your right here called a nephron. You have about 1 million of these in each kidney, and they are going to filter the blood for all these electrolytes. We're talking about everything's going to fall through, and we're going to put the good stuff back in blood, and then that yellow tube leads is what I call the rivers of urine. So we have these convoluted tubes. We're going to name all these parts. That's collected though, and these all dump into minor calyxes like here, 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 and here, and here. So it's rivers of urine. Kidney stones are when these calcium other crystallizes, this stuff in the urine crystallizes, and it forms sharp little microscopic crystals that are extremely painful. Okay. And I'll be honest with you, I think the main problem with kidney stones is probably people got screwed up nephrons. Just an anatomy thing, right? Your nephrons are not real smooth or something. Because some people, if you anybody here has kidney stones, if you have kidney stones, they're gonna give you a list of what not to eat and drink, and it's everything. Like no carbonated beverages, no milk, blah blah blah. You know, water and beer is all you can drink. And beer will help filter them out sometimes. It flushes you. I've had doctors prescribe 3 beers before you go to bed to help friends of mine drop a kidney stone. But really weird. But and of course they can just real quick while we're here, they can chemically give chemicals to dissolve it. They have lasers. They can come in the sonogram to try to bust it up. But if all else fails, they have this tool called the macro extractor. And it's like a little needle, a little hook that they run up your urethra, fish it up your urethra, clamp it, and then they pull that stone out. Quite painful, okay? Quite painful, needless to say, okay? Or very, very disturbing to watch either way if that's happening to you, I bet.
Random thing. You ever heard of riding on Big Thunder Mountain in Disney World? It helps to just.
I can see that too, yeah, shaking it out. Yeah, that's what that sonogram does. It'll shake that stone out, okay? Now, if you look at these lines in the medulla, these are probably the nephron loops coming down. So when we saw that, remember we saw a lot of lines in there? We shot red latex in the arteries, blue in the veins, and then yellow up the ureter. And so we saw lots of color out here because these million nephrons are out here, and that's a blow up of it tremendously. Okay? And stones can form up in this area, up in here, very painful. And of course, then that's going to go out to the ureter to the bladder. Okay? So know your basic cortex medulla pelvis. Okay? Very vascular, right? 1/4 of total cardiac output is going to the kidneys, 120 milliliters a minute. Tremendous amount of blood flow. Here is a step arc of the blood flow coming into this artery. Let's look at that. So it's pretty cool. So renal artery comes in and breaks down into segmental artery, into lobar artery. Now we're going up into arcuate artery. Okay, coming in, then it goes into an interlobular artery, and then branches down into an afferent arteriole that comes into that glomerulus. So at that glomerulus, we're going to have the glomerulus is a leaky capillary bed, right? And the blood pressure is going to blow everything out of that into that collecting duct. And we looked at this, y'all remember, for simple squamous epithelium lining the glomerulus, remember back in AFB1, everything falls through this small, and it goes down this proximal convoluted tubule, the loop of the Henle, loop of the nephron, back up the distal convoluted tubules that drain in collected ducts, and all collected ducts dump into these minor calyxes, into the renal pelvis where the urine collects and goes down the ureter to the bladder. Okay. Now, obviously, I'm going to talk about filtration in a second, but imagine this: as soon as that happens, everything little comes out and goes into the filtrate. Everything big stays in the blood, and then it comes out and forms a capillary bed around the whole thing to put the good stuff back in. So that peritubular capillary bed is there to pull the good stuff back in. Like you don't have any sugar in your urine. If you do, you got kidney problems, you got your diabetic, that's bad. There are no proteins, there are no amino acids in your urine. We reabsorb all the good stuff, and those are signs we looked at with that chem strip, right? That you had run to the hospital. We did one in lab 2 weeks ago where you can see what's coming out. Okay, so we reabsorb the good stuff, and then we throw drugs. You're doing some drugs. We actually actively transport, put the bloods in the urine, and then as it comes down this final loop of the nephron, this collecting duct, we actually going to use this to suck more water out, and we concentrate that urine as it goes back down as it enters into the before it gets into the minor calyx. So really, see, this is what I call the rivers of urine. Okay, but notice that peritubular capillary bed is surrounding this, putting all the good stuff back in. Now watch it come out. Then it comes out, peritubular capillary bed, interlobular, arcuate, and then backwards out the other way. Here we go. Arcuate, interlobular, arcuate vein, interlobar vein, renal vein. Thus we filter the blood. Dialysis, we pull it out of your leg, run through the plastic tubing of dialysis tubing with pure saline, and that causes all the stuff in the blood to go from high to low into the saline, right? And we just keep replacing the saline and pump the blood right back into you. That's why if you ever notice that they have to stay on the dialysis machine for 2 or 3 hours sometimes, right? It takes that long just to get enough out before the toxic levels don't keep them low in your body. But dialysis kind of makes sense now if you think about it. You're doing the same thing on a different in a machine, right, running through here, filtering out, letting the things go from high to low out of the blood and pumping it back into the bloodstream. Okay, now I'm gonna take a pause here. Is everybody okay with that? Just the basic anatomy here. And I do think, guys, look, this is one that I do think makes sense once you look at it a couple times, right? It took me at least 4 classes to understand cellular metabolism. Okay, this is one after about 2 or 3 times we read through this, this actually makes sense to me. Okay. All right, so let's go back and look at this filtration. I think we're going to see in just a minute. So this nephron, right, at the glomerulus, take a look at this. The structure around it is called the glomerular capsule or Bowman's capsule. We're going to see a filtration here, and then that filtrate is going to go and will come all the way down and back up the other end and pump out. And I knew there was something else I meant to do today. So if somebody would email me, I will bring it to y'all next Monday. All right, or if you catch me sometime, I'll hand it to you. But another thing, I don't always borrow from other books. But one of the things I don't like that she didn't do here is the book we used to use had a table here. It's a really good table. And it just showed you this is what's in blood, this is what's in filtrate, this is what's in urine. You know, like numbers of all the stuff we're talking about here. And just me seeing that kind of made me feel a little bit better. You know, it kind of made more sense to me. Okay, I wish I brought it this morning, but I just got to run it off. But I'll try to get y'all that, and I'll just hand it to you as a copy. But it's really kind of cool because you can see what's in this filtrate. It's getting absorbed, right? And then you can see the volumes coming out. Now I'll tell you that you make about 1.8 liters of urine a day. Now don't do this, but you can take it into 2 little bottles, and with some discretion, you can collect your urine probably, and that amount will probably equal what you drink today. So drinking input equals output pretty much. So if you drink 12 beers, you're gonna urinate a lot. Okay. Now, exercise and stuff that can make you go up or not, but just if you're just going through a normal day, pretty much everything else equals out. Input is that equals output. Okay. And so what's in that urine is quite interesting. Okay. But everybody got the anatomy, basic anatomy, okay with me? Let's look at this glomerulus. Okay. And I'm going to find I'm going to back up because I can draw on another page. But here is the afferent arteriole coming in, and here is that leaky capillary bed. You can see these slits in this is where everything little is going to fall through. So what I'm talking about here is what's going to fall through here. Let's look this through. Let's draw this a little bit better. Blood flow's coming through here, right? And then blood's coming back out here. What's going to fall out in here? I'm just going to pull it down here. I'm talking about what's coming out into this area. So I'm just using this as a area. Obviously, what? Water, right? Urea, simple sugars, glucoses. Pen, be like that today. Time to draw. Okay, simple sugars, amino acids, all kind of ions out there. You know what? Every freaking ion is going to fall through. Everything's going to fall through except what's going to stay in here. Red blood cells, right? White blood cells, right? If you got blood in your urine, you're in trouble. Okay, large plasma proteins, all large things stay in the blood. So all those, blood factors, coagulation factors, and all those, I'm going to say a cuss word, all those plasma proteins that help maintain osmotic pressure. Remember those proteins that are osmoregulating proteins made with the liver to keep us from getting too, dilute or concentrate our urine. They stay in the blood. Okay, so everything falls through this little, and then we pluck the good stuff back out and put it back in the blood in that pericardial capillary bed. I'm repeating myself so that maybe the third. Hey, Robin is average intelligence. Okay, about half of y'all smarter than me, half of y'all are as smart as Robin, or maybe not as smart as Robin. Okay, so I'm just right in the middle. So that means half the class should be smart as me, half of y'all should be not as smart as me, right? Not being ugly, but I got to hear it 3 or 4 times. So I'm going to repeat myself 4 or 5 times. So when you walk out here today, maybe some of this will seep in. So one more time. Is this not cool? You've got 1 million little filters here, and everything small is blowing through. And then as we go down the loop of the nephron and the distal convoluted tubules, and don't that word scare you, it's just a stupid name, proximal convoluted, loop of Henle, now called loop of the nephron, distal convoluted tubules dump in the collector ducts. We pull all the good stuff back out and put it in the blood. Right, and that pericardial, let me back up and show it because once you see it, it's really fascinating once you see the big picture. See that thing I circled, that blue capillary bed is collecting the good stuff and putting it back in, and now the blood coming out has been what? Filtered. It really is brilliant, right? Now, look, right off the bat, let's make it personal. Let's make it personal this morning. What would be one of the first problems with Robin's high blood pressure he's experienced before I got on blood pressure medicine that I should have been on 5 years ago? What do you think that does, that little capillary bed? What would happen if I took a pump and put your air pressure and just blew it up to 150. And you drove back from the Grizzlies game like I did doing the 90. And hit a ball about cold water. It's gonna blow that tire. I have probably damaged my kidneys by not addressing the high blood pressure I was dealing with. That I knew in the back of my mind I was having, right? So high blood pressure is one of the main causes of kidney failure. Because it blows these little nephrons. And then things start leaking through the shit. Think about that, right? I mean, it's kind of a cool analogy, but think about that. This is a very little filter. Okay, how many of y'all have made coffee? I'll make coffee every morning. You ever turn, I've got a bun, and I grind my own coffee, pour it in, and I do 3 scoops, and then I make 8 cups, and I drink my half, so I drink for 4 and bring 3 with me to class. But I'm a dilute coffee guy. I don't go crazy. But sometimes I have a hole in my filter, and what comes through? There we go. You got a hole in that, and then big things fall through, and you got big problems, right? I have to throw the pot away. You know what I'm saying? And then sometimes I'll get 2 filters in there, and what happens if I put 2 filters in accidentally? I got a mess. It's all over the cabinet because then it can't go through fast enough. See? So this is, to me, a great metaphor of coffee filters, because that's what we're doing here. We're filtering things out, but we're keeping the big things in the blood, that efferent arteriole, right? But if too much comes out, you're in trouble. And if everything if these clog up and don't work properly, you're toast too. Okay? Pretty cool to me. Pretty cool. Pretty cool. So yes, I think my doctor thinks I'm okay, but I'm still relatively young. When he's same age as me, so we still have this fantasy that we're young, but we're on the phone last night laughing about this, that we're not young anymore. Okay, we're older. Okay, but anyway, yeah, you need to take care of those little capillary beds, people, big time, because they do not repair. Here's what it looks like. There's some of the distal convoluted tubule, proximal, whichever, got the little microvilli, the real short things. Here's proximal. There's the loop of nephron, now called the loop of Henle. I used to be called loop of Henle, and it's going to go down, dip down. Some of these dip down into the medulla area of the structure. And so we'll see what all is going on. We go down through here, and here we're going back up. And so you kind of see the different epiphysium of each step. So we're going to then pull good things back out, and then we will actually put things into this filtrate too, like drugs we can excrete into our kidneys. Now, side note, though, we always got to have something crazy here. So here's our side note. This juxtaglomerulus apparatus. Sometimes you'll notice that the loop of nephron comes back up here and loops over right here. So there's a structure right here where the distal convoluted tubule comes back near the efferent arteriole, and it's called the juxtaglomerulus apparatus. And inside these cells, called macular cells, monitor blood pressure, the pressure coming into the efferent arteriole. So this is a self-regulatory system, okay, where if the macular cells detect blood pressure low in the kidneys, then they will produce a chemical hormone called renin, and renin then is going to go cause a whole bunch of things to occur, including the production of aldosterone by the adrenal gland that will come back here and cause you to reabsorb more water and more sodium and raise blood pressure. Okay? Which is, now if y'all remember, now look, I know we've done this really crazy, but there were 2, and we already have one big hormone that did blood pressure. Remember ADH? From the posterior pituitary, remember antidiuretic hormone goes directly to the distal convoluted tubules and causes them to reabsorb more water. Well, guess what? There's another one. So of the 40 hormones, maybe I didn't do 40, of the 25 major hormones, 2 of them do blood pressure. ADH and then aldosterone from the adrenal cortex, the adrenal gland. But that particular one gets its direction to be made from these juxtaglomerulus apparatus cells. This is a big deal called the juxtaglomerulus apparatus mechanism of renin and aldosterone production. Okay, super big important. We're going to see some pictures here in a minute that we may have showed y'all in the indica chapter, but most likely we ran through them quickly and look at them. Okay, all right. And so this is going to help control blood pressure and filtration rate. Okay, and here it is. So these cells come back right here and they're monitoring. Actually, I believe it's calcium or sodium ions coming by. And if they are low, we're going to make this chemical called renin that's like a hormone we just put in the bloodstream. And I'll wait to show you a picture of that. Involved its elaborate mechanism. It's pretty wild, okay? But they don't actually do the anatomy. They do anatomy, but they don't do the physiology. We'll come back to controlling blood pressure in just a little while and look at that picture. I should probably jump ahead and do it, but I'm scared it'll take me too long to find it. The collecting ducts usually are closed and don't absorb water, but they have them under the direction of ADH or aldosterone. They open up and water will be reabsorbed, which we'll see later. Okay, we're just doing filtrate. There's the collecting ducts coming down. Okay, there are two types of nephrons. There are the ones that dip down into the medulla. Right here, these are the big ones here, and then you have a lot of them that barely just are in the cortex, only don't go down the medulla at all. I think the ratio was rather high on one of them. 80% are only in the cortex, corticopnephrons, with 20% going down into the juxtamedullary with the big one, long ones. The little anatomy here, little anatomy. Oh, by the way, you will draw a nephron, right, on your test, right? Be prepared to draw a nephron or a file in here and label it. I can do one blind book if I don't have time to do it. I can cover my eyes and draw one. It can be a stick nephron. We're not going to get great on artistic ability. Everybody can't be as good a drawer as me, and I know that. I know that I'm artistically challenged, right? Okay, so, you know, I don't penalize those that are like me, artistically challenged, but you can do that. You draw me a little nephron and label the parts. Okay, I ain't worried about nephritis. Okay, that's bad. There's stones forming there. We already talked about that. Risk factors include diet high in fat, animal protein, check, check, Robin, and salt, check, check, and obesity, check, check, check. All of those. Okay, and that's bad, right? And there you can see the stones forming in there. That's some bad looking stuff there. Okay, now going into physiology. So we got filtrations. There are actually three mechanisms here. Y'all count that. We have glomerular filtration, right? Tubular reabsorption, and then tubular secretion. Okay, and it usually goes in that order: filtration, reabsorption, and then tubular, and then secretion. And then actually, I like to do a fourth one, come back and do some more full water out again. So but I'll just go with three, right? But in the order you'll see is usually, filtration first, selective reabsorption, then we secrete things, and come find out we secrete in almost every part of the damn thing. And then at the very end, the collecting ducts, we reabsorb more water. Okay. So look at this. So at that filtration, I did this a while ago. Look what follows through. Water and electrolytes, mainly sodium, potassium, hydrogen ions and bicarbonate, small organic molecules, metabolic waste, all exit the blood and go into filtrate. So our big urea, which is small, and uric acid and creatinine all fall out into that. Those are your three main nitrogen-containing solids in urine. Matter of fact, I usually have a question, and I was making this in a hurry. I can't believe I didn't put this on here, to be totally honest with you. Surely it's on there. Let's see. What should be one of my favorite questions? What is in urine? I guess I got in a hurry to put it on there. But what's in urine, right? Water, urea, uric acid, creatinine, and sodium and potassium. So it's very, very lots of ions, right? But the main thing being water, and then urea, and then these salts, these electrolytes, sodium, potassium. So get a little picture there. Make a mental note. I'll add that to the next year. I think I'm going to stay with this short answer questions and give them to y'all, because it gives you an idea what's important to me, right? I think this is kind of cool. And and look, if this is a freshman level class, it really, a lot of it should be regurgitated back, right? So at least you do for one day the parts, right? Or whatever, right? And then hopefully the big picture falls into place. That's what I'm trying. Then we got tubular reabsorption, where we reclaim the good stuff: water, lots of water, glucose, amino acids, and electrolytes. Okay. So super big, right back, almost 90% of all the absorption occurs right there in that phospholipid tubule. That's really where we get all the good stuff and put it back in the blood. And then all through the thing, we can do some tubular secretions. Specifically, we can secrete drugs. If you ever went to work in a bank or as a money handler at casinos, they're going to want a urine sample, right? And they can tell if you've been on crystal meth or done some heavy drugs, and then maybe they won't hire you, right? But we don't want our bankers to be, shooting, smoking, storing cocaine, right? That's not good. They used to. I haven't talked to anybody in a while, but back in the day, they would take a hair clipping at the casino and run that for. They say you can have cocaine residue if you've done cocaine for a year in your hair. So that's for a little hair clipping. Okay, I'm just saying. That's reasonable, I guess, if you want to. And they pay those guys a lot more money than they do the guy, out pushing the carts at Walmart, right? I'm just saying that's a good job over there versus entry level at Walmart. And then look, we can also reabsorb electrolytes, and these ions can be removed, and we can remove toxins like drugs and stuff out of the body and throw it in. And of course, the big one we saw earlier, remember, we can secrete hydrogen ions directly in the urine to control pH. So we have these secretions here. And so here we go. And I actually look at this, actually a nice picture here. But you can see filtration only occurs in the glomerulus. And then look, reabsorption occurs all the way across. But if you kind of look at it quickly, reabsorption, the secretions occur usually over here. Mainly here, but there are a few over here, and then we reabsorb water here. So those are your three physiological things, right? Glomerulus first, reabsorption all the way through, and secretion pretty much can occur in almost all the places too, right? So that some of our earlier books just kind of oversimplified it, because it never is as easy as we like it to be, right? We love it to be A here, B here, C here, but really those two occur all the way through it. And I admire that they're going ahead and being honest here. Okay? All right, going on, filtration rate. Now, I'm not going to spend hours on this next part. She gets into this, but this is some deep physiology. If y'all taking advanced physiology class, yeah, you'll spend a lot of time talking about filtration rate and all the factors involved. I'm just going to look at it real quick. Here's those little leaky capillary beds fenestrations. Okay, you can see that's showing what falls through, and big red blood cells, white blood cells. Look at all that stuff can't go through, right? That's very cool, very dramatic to me. There's the little openings, right? That's cool. I tell you what, I don't have time for the video. Y'all should watch the videos. They're online, right? You can go to the study area, right? And I remember watch videos. In a perfect world, I would do that, but I don't have time. Okay, but I actually think I meant to show them, but I think it's better for me just to walk on through this. Filtration rate, 125 milliliters a minute. I'm gonna run that other thing off for y'all. Filtration rate going on, and she gets all excited about this. I'm just gonna but that's kind of cool, and she walks through that pretty good. I would really watch these videos. I don't have time to show them to you. Okay, and I want to get this. This is mechanism of control. There is a self-regulation here, but here is the one I was talking about that hits home to me. The renin-angiotensin-aldosterone system is a complex system that maintains blood pressure primarily and glomerular filtration rate secondarily as a response to low blood pressure being monitored by those macular densin cells I told you want to go at that juxtaglomerular apparatus. Okay, now look what happens. It's really cool. When blood pressure drops, the glomerular filtration rate is reduced, and these cells release a hormone-like compound called renin. Renin in the bloodstream converts a plasma protein made by the liver called angiotensinogen into angiotensin 1. Now look, this is cray-cray. It can further be converted into angiotensin 2 by angiotensin converting enzyme found only in the epithelial lining in the lungs. This is like deep trivia. So this thing is not activated unless this blood goes to the lungs, right? There's probably some COVID implications here too on this one, right? And that leads to that enzyme then goes to the adrenal gland and causes aldosterone to be released, but it causes vasoconstriction of efferent arteriole and systemic blood pressure to rise, causes reabsorption of sodium ions and chlorine and water and phosphatidylcholine, and all that's going to do is raise blood pressure, increases thirst, all of which increase systemic blood pressure and sequentially increases glomerular filtration rate. Now, let me tell you what I found out when I talked to the smartest person on earth that I know, my doctor, and he then tells me this mind blowing. Your mother has blood pressure, high blood pressure problem. My mother is her doctor too. She's had it since she hadn't given birth to me in 1964. We have hereditary high blood pressure. Guess what the number one cause of hereditary high blood pressure in America is? Probably 80% of hereditary high blood pressure is this system making renin without the need to it. You're overproducing angiotensin 2, and we don't know why. He put me on, and now there's two drugs. One of them binds to prevent angiotensin 2 to be made. The one he put me on blocks the receptor for it to bind on your smooth muscle. Now think about that. If you got a water hose running, there's no pressure, but if you squeeze down on it with your thumb, you can wash your car, right? You follow me? What if I do a Vulcan grip on your hand and you can't squeeze the hose and you're going to lower the pressure? I went from 160 over 110 to 120 over 60 within 5 hours of taking a bed. Absolutely mind blowing. Silent killer. I wasn't hurting, wasn't feeling bad, didn't really feel bad at all. But I was having pretty bad high blood pressure that hit to the point where he said, monitor it and take half a pill if the top numbers goes below 120. You know, with my fat self, I probably need 120 to push the blood all the way through. But he said that's one of the that's the 80% of high blood pressure in America is you're overproducing angiotensin 2. And I asked him why. He said, we don't know. We don't know. But they're working on that. But obviously the treatment is these two drugs, one that blocks the production of it or binds where it binds to. Feel like me, think of a key fitting your car door, but now I put a plug over the car door so the key can't fit in, so nobody's getting in the car. But with that binding, that causes systemic blood pressure all through the body. Yes.
Is that like an ACE inhibitor? Is that what, like on?
Yes, the ACE inhibitor would be, I try to think what that one does. That one, that prevents smooth muscle contraction too. Yeah. But now don't forget, now beta blockers and all those, some of those have to do with different types of receptors in the heart. Like the beta blockers, those are receptor types. So that may be that. I'm not sure, but I have to come back on that. I'm not a doctor. I only play one on TV. I'm wrong. But isn't that kind of cool? Guess what? Now here's the killer. Listen, guys, $8 a month. $8 a month, and more likely, I'm gonna have a massive heart attack and run a bill of Mississippi State Insurance of over $500,000 in the next 30 years. It would be best interest of the state of Mississippi to defer that as long as they can. How many people of our family have high blood pressure and they're probably walking around and having a heart attack, and then $8 would save their life? That's scary. Get your mom to go to your doctor. Because mothers always take care of the family, not themselves, right? And if you got daddy or granddaddy, that's one they might work, because it took him 2 minutes to realize my blood pressure was high, and $8 a month seemed like a pretty cheap investment. Now, I will tell you though, that I fall asleep now at 10 o'clock. And I get up at 5, and my wife's like, this is not you, because I'm not a morning person. But by the time I go to fall asleep at 10, then I've had all the sleep I need by 5, okay? Okay, but it has been kind of weird, but I don't feel any side effects of it, other than getting sleepy now. Here it is, great picture, look at what all it does. So here's the renin, and look, and it goes, angiotensin comes down and does all of these effects, including the production of aldosterone. It's going to raise blood pressure, right? It's going to go and cause blood pressure to go up. Tells the brain that you're hungry, thirsty, so you'll drink. That raises blood pressure, because drinking more raises pressure. But here's what's killing Robin. Vasoconstricts the smooth muscle off of the body. So all my blood pressure was going up. Now, if I lose 50, 60 pounds, it would help too. So he did say if I go back to the gym and lose 50, 60 pounds, I'd probably have to go off that pill. Or not. He said it probably could be hereditary. He's not 100% sure, but since I have a history of that, and I have the body of my mother and I have her needs, he assumed I have her high blood pressure hereditary, possibly. Hey, let's watch this. Maybe this one little video won't kill us. Sorry. This might just show us the end of it. I like the viewing.
The most easily adjustable factors that regulatory mechanisms can influence to maintain the GFR is the diameter of the afferent and efferent arterioles. The afferent arteriole brings blood to the glomerulus, whereas the efferent arteriole drains blood away. Think of the glomerulus as a sink that you want to keep full in order to maintain filtration. The afferent arteriole is the faucet, and the efferent arteriole is the drain pipe. Factors that reduce the GFR, such as a low systemic blood pressure, which results in a low GHP, cause less filtration. This is because the sink does not contain enough water. How can you fill it up again? By opening the faucet and plugging the drain.
This is
This
what our body
is
does.
exactly what happens in the kidneys. The afferent arteriole is dilated to allow more blood into the glomerulus, and the efferent arteriole is constricted to create a backup of blood in the glomerulus. Therefore, we see an increase in the glomerular hydrostatic pressure and the GFR. The opposite is also true. If the blood pressure and GFR are too high, homeostatic regulation can decrease the pressure in the glomerulus by constricting the afferent arteriole and dilating the efferent arteriole, or turning down the faucet while opening up the drain. Next, let's quickly examine two of the major regulatory mechanisms and how they control the GFR. First, local mechanisms initiated by the kidneys respond when the GFR drops too low or rises too high. These local mechanisms are an example of autoregulation and work by adjusting the diameter of the afferent arteriole. A second regulatory mechanism is hormonal regulation of the GFR, which is part of a larger system that controls systemic blood pressure. Low blood pressure and a low GFR result in activation of the renin-angiotensin-aldosterone system. Renin is released by juxtaglomerular cells of the afferent and efferent arterioles, which results in the multi-step activation of the hormone angiotensin II. Angiotensin II increases blood pressure by multiple cardiovascular and renal effects. In the kidneys, it causes constriction of the efferent arterioles. It also causes reabsorption of sodium ions and water, both directly and indirectly, through the release of aldosterone. Water reabsorption results in greater blood volume and therefore a higher pressure and GFR. Interestingly, the hormonal response to a high blood pressure and a high GFR leads to an even further increase in the GFR. High blood pressure causes the release of a hormone called atrial natriuretic peptide, or ANP, which opposes the effects of angiotensin II and lowers the blood pressure. In the kidneys, ANP causes dilation of the afferent arteriole and constriction of the efferent arteriole to raise the GFR. You might ask yourself why we would benefit from a further increase in the GFR. The answer is that a high GFR means increased filtration and therefore more fluid loss. More fluid loss causes a decrease in blood volume and effectively lowers blood pressure. This doesn't come without a price, as chronically high blood pressure can result in kidney damage.
Okay, that's pretty wild, right? So it's very complicated little organ here, but that's kind of cool to give you a taste of how that works, okay? Now, what I'm gonna do is I'm gonna stop here and I'll finish this later on Wednesday, and I'll put that up, so we'll have a part 1, part 2 for this chapter. Is that cool? All right, guys, let's end it, and y'all have a great